Hi, in this video, we want to take a look at Lasso, Ridge, and Elastic Net regression for supervised learning. Now, these are called the regularization methods of finding coefficients. All right, so previously in another video, we talked about regular old multiple linear regression. In that situation, we're finding the line of best fit. So we're minimizing the sum of squares. Here, we're going to modify that. What we're going to do is that we're going to, in a sense, put a penalty on the accuracy of my model for the size of my coefficients. So if I have large coefficients, then I'm going to interpret the model as like being less accurate than if I was using regular multiple linear regression. And so the reason why we do this is that this prevents overfitting, that this will mute out the coefficients that they don't overfit. This is advantageous when I have correlated variables with each other that are in my predictors, or if I just have a lot of predictor variables, just in there, that it will mute out, a bunch of them so that things don't go like unreasonably large. One thing that you'll notice if you look at the math equation of multiple linear regression, if I just happen to get large values for a bunch of x's, I'm going to overshoot a reasonable value for the predicted value. And so the regularization prevents that. Now, something that is important to remember is that Lasso is minimizing the L1 norm, that's the absolute value norm, and this will actually push out predictors. They'll actually assign a coefficient of 0, which effectively means it's not there. And ridge regression minimizes the degree 2 norm, the 2 norm, and there it will always keep, at least even if it's really, really small, it will always keep every single predictor variable. I personally used ridge regression for the purpose of building models when I had either stakeholders or legal requirements to make sure that I had predictor variables in my model. Lasso, you can use that for variable selection. Now, ElasticNet is somewhere in between where we actually combine Lasso and Ridge in a weighted manner. So when we have high dimensional data, so here I mean a lot of predictor variables, or when we have correlated predictor variables, multicollinearity going on, regular linear regression can have problems. And so we want to use regularization to address these problems. So in regularization, we're penalizing the error of our evaluated model by the size of the coefficients. Larger the coefficients, the more the error. Now, the penalty term is something that we're going to have to fit. That's going to be another parameter to figure out. All right, so we're going to run through some examples. So first and foremost, let's go ahead and set up the workspace. I'm going to make it so that I don't get a whole bunch of digits printed on the page. I'm going to avoid scientific notation if I can. I'm going to suppress warnings that just aren't really that important. I tend to do things that break non-standard standard evaluation. I go back and forth. That can create warnings that really I know about. They're not a problem. And I'm removing any artifacts from my workspace that might interfere with my code. And I'm going to be piping in the tidyverse, so I'm using the Magritter package. Now, once again, I'm going to use the prepared house prices dataset. So from Kaggle, there is a competition for regression with house prices. I've done the data prep. If you remember from that video, I used Boxcox, Yo Johnson on some of the numeric variables, used Boxcox on the target variable, and I did binary binning on the categorical and ordinal variables. All right, so in that data set, we have a lot of predictor variables, and here are all of the prepared predictor variables from the data sets. And if you look closely, these are not the original names of them. I passed the names of the predictor variables that was there through the Janitor function to make things. I like to always have standardized names. I use Janitor's make clean names function to do that. So like here, you'll notice that anything that was like a punctuation symbol, numbers on the left, the beginning of a name, it's been modified. And there's other things if you look through, you can find differences. All right, so now something that is important about regularization is that I'm going to assign a penalty for every single coefficient. Well, imagine if I take my linear regression model, I have a regular old linear regression model, and then I take one predictor variable, I multiply it by 10, I take another predictor variable, I divide it by 10. Okay, so what will happen is that when I multiply by 10, the coefficient is actually going to divide by 10 if I refit the model. And the other one, where I divide by 10, the coefficient will multiply by 10. And the informative value, the predicted value, won't change. This is, if you watch my linear models playlist in YouTube, I go over the proof of this, that rescaling a predictor variable does not change the predictive value of the model. And so if we think about that for a moment, well, I can multiply a predictor variable by anything, get the same predictive value. In terms of regularization, if I was to go through and multiply predictor variables by 100, let's say half of them I multiply by 100, well, in that whole penalty scheme, the system, because of the penalty, will want to shrink those down more than than where the coefficients would end up being smaller. And so, if I divide by 100, those predictor variables will be like more prone to getting kicked out. And so that's something to be mindful of. And so I want everything to be on the same scale. So I'm going to rescale this. Now here we just need to divide by the standard deviation, but I'm going to go ahead and subtract off the mean, the sample mean, and divide by the standard deviation. So one thing when you do this, when I have my training data and my future scoring data and validation and tests in the middle, I need to do the same data prep. And so something I need to do, I need to save the averages that I subtracted off, and I need to save the standard deviations that I divided by, so that when I get data in the future, I can make the same data prep going on. And so here I'm just showing how we can quickly get the column means and the column standard deviations. And so here, this is what I'm dividing by, all these values down here. And so after I've done this, after I've done the scale function, now all of my predictor variables have a sample mean of 0 and a sample standard deviation of 1. All right. Now for variable importance in a linear regression model, the standard way is to use the t test statistic, or the absolute value of it, to indicate importance. Well, in a regularization model, I've already done my rescaling, and we're working to shrink things. So the size of the coefficient more directly corresponds to variable importance. So we'll go ahead and accept the coefficients, the absolute value, as being the variable importance. So the larger the coefficient, the more important the predictor variable, and that's absolute value, larger value. Now, there's some parameters I need to introduce in addition to the coefficients for the predictor variables and the intercepts, because we have a penalty term, but we also have a lasso, elastic net, and ridge term. Okay, so the lambda I have here, this is the regularization strength. The higher the value, the more penalty I put on my model in terms of error for the size of the coefficients. So high lambda, my model is going to work to have smaller coefficients. Small lambda, then like let's say 0, it's not going to try to shrink my coefficients at all. And so if I put it down to 0, I'll have a standard regression model. Now the alpha, this is a mixture. This indicates a mixture of elastic net. And so if I put 0 or 1, I'll get lasso or ridge. If I put something in between, I get a combination of those two. And it's going to, the amount of combination will be determined by the alpha. And so when we're evaluating, or when we're fitting our model, we need to determine our lambda and our alpha for this. All right, so let's look at ridge regression. Ridge regression minimizes the 2 norm. So here you'll notice I've got a square going on here. I'm taking the coefficients from my model, and what I'm doing is I'm squaring the coefficients, adding them up, multiplying by that lambda that we talked about a moment ago, and then I add it to the error term of my model. Okay, and so that is my measurement of how good of a model I have. And so something about ridge regression is that ridge will never 100% kick out a predictor variable. This is very important because I'm in situations as a data scientist where maybe legally I have to keep a predictor variable, which I've had that like year after year at my previous job. Uh, for legal reasons, I had to, this was an HR work, I had to include all these predictor variables. But I looked at the predictor variables and went, oh my gosh, these are collinear with each other. It's a bad idea to fit these models this way. And I could see it. I knew there would be overfitting. Ridge regression helped me out. Now, another reason why I would be in that position, maybe my stakeholders just absolutely insist on certain predictor variables being included in the model. I look at it, I go, hey, I have multicollinearity. Now, multicollinearity, if I have enough data, really isn't a problem, but maybe I don't. Maybe I don't have enough data for that. And so ridge regression can like save us so that I can build the model that they want, and I am, I'm keeping everything legally right, but I'm making sure I produce a good, solid solution for my stakeholders. All right, so to implement this in R, we're going to use the glmnet package, and it's a namesake function to fit. Now, here I have to already know my alpha. I have to already know my lambda. Alpha of 0 gives ridge regression. Alpha of 1 gives lasso. And here I chose 0.5. I played around with, I'm going to show how I did that. I did cross validation, and I determined a reasonable lambda for this particular data set. And I went ahead and fit it. Now, in this, you'll notice that I specify my predictor variable, data frame, and I specify my target variable vector. This is different from the LM function. The LM function, typically we pass in a formula and then the data set. Here, we have two data parameters that we're entering. And there are also a whole bunch of other parameters that we need, but these are the fundamental ones. And so we get an indication of degrees of freedom and the percent of the deviation accounted for. And to get the coefficients, this is a little bit different than the LM function. That if I run coefficients, then it's going to give me something that's not quite the same as a data frame or a matrix. And so to make it into a matrix, make it so that it, or make it into a data frame, make it so that it works better with the rest of the R community. I go through and I just pass it into as.matrix, as.dataframe. It gets produced as a special type of sparse matrix. And it's really, like if I just want to print it and look at it, that the coefficients for a glmnet function are fine for reading, but for the purpose of, maybe I want to do some other analysis, maybe I want to do a bar plot, something like that, it's really not the greatest presentation. Pass it into as.matrix, pass that into as.data frame, and then I can start doing regular old, R stuff. And here I went ahead and sorted by the coefficient size. And now here I'll have the most negative up top, most positive down at the bottom. So if I want to look for the most positive ones, I have to look at top and bottom. The middle is where I'm going to have the least important predictor variables. So basement exposure is a major like red flag. Like you see basement exposure, then we know that we're going to have lower home value price. Also roof style. This one I believe is a binary binning. So roof style looks like certain roofs are much more valuable than others. While if we scroll all the way down, I'm good, man. Thanks. I'm good, thank you. Yeah. One of my buddies, I'm at Skydive DeLand right now, and I'm going to be jumping in a little bit, but good guy. He's looking out for me. All right, so now the one that the coefficient that is the most important is the size of the living area. That sounds reasonable. And so as I look through, one thing I like to do when I have a model like this, go through and just kind of look to see, does it make sense? Does living area seem like that's the most important? Well, that's like the main statistic that you see when you look at, Zillow is like, what's the size of the living area? Watch House Hunters International. They talk about the size of the living area that the people were in before and where, what they're moving into. Now, lasso regression. Lasso is, similar to ridge regression, but now instead of squaring the coefficients, I'm taking the absolute value, then adding them up, multiplying by lambda, and then I add that to the error term. And so here, let's get the how this will work out. This will end up. This will actually set a coefficient of equal to 0 in this model formulation. Why do we like that? Because that does our variable selection for us. If we go up here, if I'm looking at ridge, let's see, how low does it go? You'll notice that we never actually achieve a 0 for any of the coefficients. Sale condition is super, super small. That's probably multicollinear with other predictor variables, by the way. But sale condition never actually reaches 0. All right, so sale condition is probably an important predictor variable. If it's a fixer upper or a not, if ready to move in. So that I would anticipate if I dug into this, sale condition is probably multicollinear, and there's something else like with it that's causing it to get shrunk down. All right, so when we do lasso, lasso is very similar, but this time I set alpha equal to 1. Once again, I have to know my alpha, I have to know my lambda if I'm using this version of the function from the GLMNet package. And so we'll notice that we got degrees of freedom of 25. That's like less than a third. And we've got about the same deviation percentage. When I look here, now check this out. Check out all of the zeros I've got going on here. I mean, it's a whole list. I've pushed out a lot. Look at that. Look at that. So like a whole bunch of them are just gone. Here we have living area once again is the most important. Then of the negatives, basement exposure once again. So, this is giving me a good idea of what are the important variables for pricing a home. Now, elastic net is where we combine the two. So what we're going to do here is that I'm going to use this alpha to do a weighted average of the two aspects from ridge and lasso. So here you'll notice that I'm doing the squaring of the coefficients, and I'll do the absolute value. And so here, what this is doing is this alpha gives me the ability to combine both of these to try and get a better fitting model. And so I just have to specify a non-1, non-0 alpha value, any value in between. And now we have to work to figure out what is the best alpha, though. And you'll notice because of the ridge aspect, I never actually hit 0. Now up to rounding, they get rounded down because of the weighted aspect. Or not rounded down, but they get rounded off. They get rounded off so they look 0. Technically, they're not, because in the ridge model, every coefficient is non-0. All right, so now to actually figure out what is the actual lambda, what is that penalty weight, what I'm going to do is I'm going to use the cross-validation GLMNet function. And so here, what we're going to do, we're going to do cross-validation, and we're going to try and find what our lambda should be. Now, a drawback of this is that we need to figure out what our alpha is before we do this. So step 1, identify your alpha. If you know you want ridge, if you know you want lasso, if you know you want a particular value of elastic net, we're good. But if we don't know the alpha value, we have to kind of figure that out. Um, yeah, a lot of people like online, a lot of people who talk about machine learning like Lasso a lot more because it does the feature selection for us. um, I feel like the people who talk about these types of models have a blind spot for the requirements of actually launching a model in real life, specifically when I have legal constraints or I have stakeholders who force like certain aspects onto my models. It's common in the workplace to see people right out of college like being like super rigid on things like that and unwilling to include certain models. Um, you can get yourself in trouble pretty easily by being rigid. Do whatever your stakeholders want, period. All right, so now this function identifies two lambdas for us. It'll actually give us a whole range of lambdas, but there's going to be one that gives us the minimum penalty, and there's going to be one that gives us the largest lambda that is within one standard error of the minimum. So there's a minimum, but then the function's going to go like, hey, let's increase lambda from the minimum by one standard error. And what is that? And so here, this is the lambda that gives me the minimum, and this is the lambda that gives me one standard error away. You'll notice that that's close to 0.5, which I chose 0.5. I always try to choose parameters that are easier. Going like 0.494, like that, it just won't feel right when I present this to my stakeholders. Now here's the range of what we've got, and we can see that the mean squared error is what I chose in on this to evaluate. I could have used mean absolute error. There's a whole bunch of different metrics, but we can see in this range that the error isn't quite as good with the one standard deviation rule, but with a larger lambda, I'm shrinking down those coefficients. So I'm protecting myself from overfitting by quite a bit. Now we can do the same also with Lasso. We get the same values. We get a minimum, and we get one standard error to the right of the minimum. And you'll notice when I was fitting the model, I put 0.25, which is a relatively round number close to here. And so here we can see this is where the minimum is. This is one value to the right. And so, that's looking pretty good. Now, elastic net, for this one, I just chose 0.5 because, hey, I don't know what would be best. So I just ran with it. If I was doing this for a real project, I would definitely try a whole bunch of alpha values. I would do a grid search. And we can see the values here. Yeah, so our two choices off of the CV GLM net function is to take the one that minimizes the cross-validation error, or the one that's one standard error away from lambda that gives us the minimum. And remember, this is going to be going to the right. This will be a larger lambda value. And the reason why we like this one is because larger lambda shrinks down the coefficients more. So if you look at those plots, by going to the right, I haven't really lost a whole lot in terms of accuracy on there. I'll scroll back up to show this. Notice that going from here, which is the minimum, to one standard error to the right, yes, I have a less accurate mean squared error, but not by much, right? I mean, it's pretty close. And I'm looking at this, I'm going, hey, this might be a little bit better because here, this is going to push out coefficients. It's going to shrink them down a lot more. So I'm more protected from multicollinearity, from redundant predictor variables, and overfitting. Oh, and to extract these, what we do, we just take our cross-validation GLM net object, and then it's lambda minimum and lambda one standard error, and it's that. So that's how you extract it. That's how you find it after you've done the fitting. All right. So we've talked about ridge, which minimizes the degree 2 sum of the coefficients, and Lasso, which minimizes the absolute value sum of the coefficients, and Ridge will always keep all of your predictor variables. Lasso will kick out some predictor variables. And the larger my penalty term, the more the coefficients will shrink. And in Lasso, the more predictor variables will get kicked out with larger lambda. Elastic net is a hybrid of the two, a weighted average of them. All right, well, that's all I've got for you. Life is short, do math. Fucking kidding me.